We're going to talk about prime numbers and a few prime number theorems that'll be helpful. But before we get started, let's just take the number 72. Okay, 72. How many? Can you tell me what the factors of 72 are?
2 to the third and 3 to the 2.
Yep. You said 6 times what? Or 9 times 8? Sure, 9 times 8. And I'm going to go in this direction here. 8, 9. And then can these be broken down?
2 cubed.
Yeah, 2 cubed. 2 times 4 and 2 times 2. And what's 9? 3 times 3. So what do you call these numbers when you can't break them down into anything else? They're called prime numbers. So one of the things you're going to learn today is that all numbers are fit in one of 2 categories, at least in the integers. They're prime numbers or they're composite. There's nothing else they could be. Now, it puts prime numbers in the driver's seat as being pretty important because if things are either prime or composite of primes, that means every number is made up of what? Primes. So you can see why mathematicians were so interested in primes. But I got a question for you. If you look at 2, 2, 2, this is the same as 2 to the third times what? 3 to the second, which is kind of an interesting looking number. Now here's what I want to know. How many factors are there in the number 72? Yeah. 12? How'd you get that?
3 plus 1.
Oh, you're getting way ahead of me, Elliot, but thank you. Yeah. If you listed them, you'd have 1 and 72. What's another factor? 2 and what? 36. 3 and what? 24. 4? 18. Yep. 5? 6? Yes. 6 and? What's that? 12. And anything else? There's one we haven't listed yet.
8 and 9.
Yeah. 8 and 9. Yeah, 8 and 9. So if you list these, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's a total of 12 factors, including 1 and 72. Well, there's a way that you could count them, and Elliot got us there already, but that's fine. Let's take the number 9. How many factors are there to 9? Well, we have 1 and 9, and what else? 3. How many factors to 8? 1 and 8, what else? 2 and 4, anything else? No. What do you notice about this number of factors and this exponent of 2?
It's greater than.
Greater than. This is 1 more than this. What do you notice about this number of factors and this exponent? Yeah, it's 1 more. So if you have 1 more for the 8, which was 4, and 1 more for the 9, which were, or 1 more for the 8, which is, what did we do there? No, I'm sorry. We have 3 for this one and 4 for this one. 1 more than 3 is 4. 1 more than 2 is 3. 3 times 4 will get you that. So could you come up with a formula that could tell me how many factors in 70 in any number? A. Can you give me a formula? Well, in this one, it's n1 plus 1 times n2 plus 2. And then for any number, it's going to be what? Or n1 plus 1, n2 plus 1, yeah. And then it's n, we could go maybe ni plus 1. It depends on how many different prime numbers there are. And that's how we can figure it out. Let's check this out real quick. What are the factors of 24? See if you can figure out how many factors there are in 24 as fast as you can. break this down into primes. This is 2 to the third times what? 3 to the first. So you're just going to go 4 times 2 is 8. Got it. And so this is going to be 1 and 24, 2 and 12, 3 and 8, and 4 and 6, which gives me the 8. Isn't that neat? So there's prime numbers for you. Some cool things going on there. One last thing I want to ask you about is let's take a weird number like 47. What are the factors of 47? There aren't any other ones, are there? It's a prime number. But we might want to check it. So I could see trying to divide it by 2, and that's not going to work. What's the next prime number after 2? 3. Is there a way to check to see just real quick if this is divisible by 3? Yeah. Add the digits together, and if it's a multiple of 3, it's divisible by 3. Do you know why that is? You're going to prove it next week when we start in modular math. Yeah, you're going to prove it next week. Yeah. It's an easy proof. You'll love it. It's one of my favorites. How about divisible by 5? No. How about divisible by 7? Nope. How about divisible by, what's the next prime number after 7? 11. Nope. How about 13? So how far do you go up? Half? Not half. Oh, why do you say square root?
Because anything above the square root has to multiply with something below the square root, or is it equal to?
So that's exactly right. So let's say we took the square root of 47. Would you with your calculator? Is that around 6.8? 6.9? 9, okay. So this tells me that as soon as I go to bigger than 6.9, what will the other factor be? Below. So if one is bigger, the other one's going to be below. So if I tried 11, yeah, it might not, I might find something divisible by 11, but I would have already checked something probably close to 5 or 3, okay? So what we do is we take the square root of 47, and we don't go any higher than this for primes. Prime check will be 2, 3, 5, and we don't even have to check 7 because 7 will be too big. And we find that none of those will work. So those are the things that you kind of know about, and we're going to look at as theorems. So here goes the first part. When we talk about a prime number, what we're talking about are numbers greater than 1. Now, why isn't 1 a prime number? Yeah, every prime number, like, let's say 5. How many factors are there of 5? 2, 1, and 5. So how about 3? 2, 1, and 3. How about 2? 2, 1, and 2. How about 1? There's only 1. So by definition, 1 is not a prime.
Is 0 a composite?
It is not a positive integer, so we're not looking at it. All right, so an integer greater than 1, and that's also not greater than 1, is said that is not prime, is said to be composite. So here's what I want you to just remember. You're going to see this word a lot, composite. That's a number made up of primes. Okay, so it's either a prime or a composite. When p is greater than 1, we don't include 1 because it's not a prime. So for integers a and b and prime p, a prime number that's divisible by a product of two numbers. Either a is a prime or b is a prime. Could they both be primes? I said that wrong. Either p is divisible by a or p is divisible by b. So let's say we say 3 divides, yeah, you'll need to finish that quiz, Alex. 3 divides, oh, let's say 18, okay? 18 is probably a bad example. Let's say 15. 15. So if 3 divides 15, 3 divides 3 times 5, okay? So for integers a and b and prime p, if p divides 3 and 5, would it divide both of them? So what if you had, so divide this, and then this number was 6. Could it divide both? What's that? Right. Then this is really 3 numbers multiplied together, isn't it? So it's a and b. You have integers a and b and prime p. P divides a or p divides b. So what the idea there is that we can prove that by saying if p divides a, the proof is complete, okay, because then one of them is prime. But suppose p isn't dividing a. P does not divide a. So p doesn't divide a. A and b are relatively prime to each other, so we can say the GCD is 1. The linear equation for that, a times a constant r, or an integer r, plus p times s is equal to 1. And that's your equation, your linear equation from the GCD, where r and s are elements of the integers. Okay? Now what's cool about that is then b is equal to b times 1, which it always is, and we can now replace 1 here with ar plus ps. So b times 1 is b times ar plus ps, and then when we multiply those out, I'm going to get, abr plus bps. Now, originally we said p divides ab, so which is bigger, ab or p? AB. So AB is going to be equal to K times P, where K is an element of the integers. So if that's the case, we can replace AB here. And so I get B is equal to KBR plus BPS, because I replaced AB with KP. Am I doing okay? Doing all right? Little clunky, but it's working. What can I factor out of these two? P. So P times KR plus BS, where all of these are constants. K, R, S, B, all of them are constants. Then if B is equal to this, what can we say about P and B? P divides B. And so since that's the case, P is either divisible by A, or if P isn't divisible by A, we just prove that P is divisible by B. That kind of makes sense.
Are we supposed to try and find something like that, or we have to like substitute credit for one?
They're just kind of making a statement about two integers, and they're saying if you have a number like 18 and 5, and you're looking at 3 dividing that. 3 divides 5, or 3 divides 18.
I don't know, but we have to like write truths like that?
Oh, like this?
Yeah.
Sure. You could do that. I'm just showing you where this came from. If P is a prime, then P is divisible by A1, A2, A3, dot, 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 A of n. So what they're saying then is that P is going to divide any one of those, either this one, or this one, or any of them. So we're saying if P divides the number, it's going to divide one of those factors. So they use P divides 6 times 11 times 24. P divides 6. P divides 11 or p divides 24, there's at least one of those that's divisible, and there was. And they did a little math induction. I don't think it's a super helpful one to work through. This one's a little annoying in that we're talking about something that seems pretty important. Fundamental theorem of arithmetic. It's the basis of all number of integers. And when you talk about integers, anything greater than 1 we said was the weird one, and probably 0 would be 2, is that it's either prime or a composite. So what they're saying is every number is either a prime number or a composite number. It's one or the other. And all numbers are made up of primes, since composites are made of primes, and primes are primes. And that's really all there is to say about that. And we're going to do a bunch of factoring, but I do want to bring up this last part down here. Last theorem is what we've talked about already, is if you want to check for these, just look at all the prime numbers less than the square root of the number itself. That's as high as you need to check, because as soon as you go over, then you're going to be looking at earlier ones. And that's kind of what the proof is talking about. If you try, for example, 25, okay, the numbers you would try would be 2 doesn't work, 3 doesn't work, 5 and does work. What if you tried 7? 7 times what is 25? Well, it's somewhere between 3, and you've already checked between 3 and 5, so it makes no sense to try 7. So you just look at the square root. Do you see why it's not half? All right. Yeah, but a half of it. Let's go to the problems right away. We're going to do a couple of these and get you started here. It says, determine which of the following are primes. So take 143. What should we divide 143 by? Won't make 2. Won't make 3, because 4, 5, 8. Won't make 5. Does it divide by 7? No, because 14 it is. Divisible 3 it's not. How about 11? Yes. 11, and then what is 11 going into 143? 13. And right there, you kind of know that 11 times 13, you don't need to try anything bigger, because what's the square root of 144? What's that? 12, right? So you know that it's less than 11 as far as you need to go. This is not prime. Let's try the next one, 199. Does 3, well, tell me what the square root of 199 is. I need your help. How much? 14.1. Okay. So let's try 2. Does that work? How about 3? No. How about 5? No way. 7? 259? Nope. How about 11? Nope. And should we try 13? Yeah, let's try 13. 13 works? No, it doesn't work. Do we need to try 17? Nope, it's too big. So therefore, this one is a prime. You tried 223. All right, let's go to the next one. It says, prove that 2 is the only even prime. Seems obvious, doesn't it? So how would you prove it, though? Any even prime number greater than 2 is going to be what? It's going to, it is a composite of 2 times whatever that number is. And so therefore it's not a prime.
You didn't even have to prove it?
That's proving it with words, yeah. You could do that. Let's take these numbers. Which of the following repunits? I think it's rep units. I don't know what it is. No, it's not binary. It's just the number 11. Is 11 prime? Oh, yeah. 11's prime. How about 111? That's divisible by 3, isn't it? 3 times what?
I don't care.
37? 37? So not prime. How about this one?
11, 101.
This is 11 times 101. So this one is not prime. Yeah. You sure? I agree. I agree. Check this one, though. Check this one. I'll leave that one up to you. Go to number 4. Be ready to be dazzled. Sometimes proofs are really pretty cool. And if you look at this one, show that if P and Q are primes, and P divides Q, then P has to equal Q. And we're saying this for all numbers and all primes. So which is the larger, P or Q? Well, yeah, but we're going to correct. Q is going to be equal to P times 1, right? Or P times K, P times K, where K is an element of the integers. And it would be positive integers, yeah, because we're not looking at 0 or negatives. It's actually greater than 1 is what it is. So if this is the case, what if K were 2 or 3 or 4? If K was greater than 1, then it would be a what? It would be a composite. Therefore, K has to be equal to 1. So then Q is equal to P times 1, which is what? Q is equal to what? Q is equal to P. Isn't that neat? That is a neat, simple, but revealing proof. Find the prime factorizations of these numbers. So let's do it. 9, and from here on out, I'm just going to let you work on these. This ends the video.